I just wanted to say that I was at the Capitol Audio Fest and saw JR's first seminar on cartridges, styli, alignment tools, etc., and was really taken with it. And he had another seminar the next day and talked about and had a whole hour of on totally different topics. And then he had a presentation in the room, Larry Borden's room, which was Gary Coe of Genesis and Merrill Audio, Merrill Wedesinga. And he new things came up in that. So I was just blown away by how much good information JR had, and both in his products and in his future developments and in the research he's doing. So JR, if you want to unmute yourself, and I see you are.
Can you hear me?
Yes, I can. Thank you.
All right.
So to start things off, I want you to get into your presentation as soon as possible, but can you just give us a little bit of background on yourself, how you got into this and what Wally Tools is?
Yes, yeah, okay. Thank you. And thanks for spending this time with me tonight. I love talking about this stuff, and I think you figured that out in DC. So I've been an audiophile since 19. I'm 52 right now, and met Wally. I lived in Minneapolis, St. Paul, was born and raised there. And that's where I met Wally, probably 28 years ago. And we started a fast friendship, and I realized that in Wally, I would learn a lot. And one thing people don't know much about Wally is that they certainly know him for being an analog guru. He was a acoustics guru as well. I know a lot about acoustics. Psychoacoustics, and so he passed away in 2018. I made a few of his products for him, not much. Wally wasn't much of a business guy and would far rather have conversations with audiophiles and do research and studies than actually make tools and ship them out and cash checks. When he passed away in 2018, we found thousands of dollars of uncashed checks in his house, all over the place. He just he didn't have that organizational acumen, and he got pummeled for it online, rightly so, for taking payments and then not shipping it, which is why he started a policy of, look, don't send me any money orders, only personal checks, and hopefully I'll cash it, right? So he died in 2018, and I had no plans to do anything with this. But one day I was talking to his son, Andre, who is the head of R&D of Medtronic, and mechanical engineer of his own right. And I said to him, you know what? I loved your dad and I loved what he did, but there was so much more to do. And I'm interested in doing some of it, and we want to do it together. You can be my engineering check and resource. And so there we went. I didn't expect that it would get into all these new products this quickly, but the more I learn, the more I realize how much I don't know, right? And so then I go down that path. So what's going on down here? And I go down that path, what's going on down here? And so you're going to see some of those new paths today in this presentation.
All right, great. Now you said you would like to go over some of the stuff you did in the first seminar at the Capitol Audio Fest.
Yeah, there, you seeing it?
Yay!
Okay.
All right.
All right, and apologies for those who have already seen this, but it is dense material. There's a lot there, and even if you have seen it, maybe it'll be refreshed on some things. I did add that element on the impact of skating force on cantilever angle video in here, so that was from day 2. So let's see. Here we go. So I just want to set expectations for this seminar. This is advanced level material. I'm assuming that you've got knowledge on how to set your overhang, how to set your cantilever alignment, your vertical tracking force. I assume that you know how to affect, but perhaps not measure your azimuth and rake angles. And I assume that you know the difference between a fine line contact stylus and a conical or elliptical. All right. Moving forward from there, if there is some background, perhaps we can take some that you need. Maybe we can take some time for that. But I'm going to go headlong into the material. I'm going to cover the what and the why, and I'm only going to direct you to the how. I'm not going to do it. I'm not going to do the how you do these things on the on this. So let's start with how a lacquer is cut. This is a great little GIF that I found online at Vinyl Recorder, how a right channel signal is cut. And as you can see, the cutter head stylus is cutting at a 45-degree angle, right? So left channel is just the opposite. And then you can see an illustration. Oh, let me turn on my, I'm going to turn on this little function here just a second so I can annotate with my spotlight. Okay, see my arrow?
Yep.
All right, and so this is what the groove would look like, right? Back to the next frame. Stopping here. I guess I got to stop it. Okay. Mono. Both of them are working together, and it makes a perfectly, when a mono signal is cut, it makes a perfectly horizontally modulated groove. Again, look at the top down. That's the illustration to the right. Now, if there's an instrumentation in the center between your two speakers on a stereo recording, maybe it's a voice of a singer or something, and it's right between your two speakers, that is done with a horizontally modulated groove. Okay. Next, the stereo. So stereo, it's going to be obviously all over the place. It's a miracle that we get what we do from these tiny little grooves. And I'll show you. Here's a photograph that I took I used my lab microscope of a portion, a high frequency portion of the Audiophile test records frequency suite. So this is probably somewhere around 18,000 hertz signal, at least according to the I didn't measure it frequency wise, but you can measure it mechanically here. And gold star if anybody can catch the error, because there is one. This was taken by tilting the microscope at a 45-degree angle and looking directly at the left channel wall only. All right. Now, do you see these? And I'm going to turn this on again. Do you see these undulations, these horizontal undulations? That is effectively a sine wave that is mechanically imprinted into the groove, and the left channel contact edge of the stylus is going to hit those. It's 11 microns peak to peak. Now, just to give you an idea of size here, relative size, in this entire frame, you could fit the diameter of a human hair. A human hair would fill up that frame completely. The human hair is about 100 microns. Maybe Nordic hair is narrower than that, but the average human hair is about 100 microns. So about 3,700 magnification here. It is a miracle that we can actually we can read these tiny, tiny signals and hear it as music. Now, I'm going to come back to this a little bit later. So there is, looks like I always have to turn off annotation to move to the next screen. Okay. This is going to be relevant. So I need to go over real quickly the anatomy of a stylus. And again, the annotation. There are two radii. This is the major radius. You see my marker?
Mm-hmm.
Okay, that's the major radius. Actually, it's more down here. That's what matters, because the part that touches the groove is probably right about there and right about there. So there's a radius here. All right, that's called the major radius. Now, the minor radius. So the minor radius, again, right here. Minor radius on a fine line contact stylus is anywhere from 2.5 microns to say about 5. After that, it's getting a little thick. I'll go over why later on that's a little thick. So on the major radius that we just looked at, you're looking at between 40 and 70 microns. Again, you don't need to remember these numbers, but it's going to be relevant a little bit later. Okay. So there are three, everything that I've been doing for so far with Wally Tools is to optimize the 3 orientation axes. Now, Azimuth, I think everybody knows what Azimuth is. Zenith, I wish, what if I'm going to stop the share just for a minute. Does everybody see me on their screen?
Yeah. Yeah.
Okay, you see this model? All right. So this is a 1,000 to 1 scale model of a groove and a stylus. So Azimuth is this axis, although we'll find out later it has nothing to do with the stylus, but it's this axis. Rake, of course, backward and forward, that would be tantamount to raising or lowering your tone arm. However, a lot more happens when you raise and lower your tone arm. Again, I'll go into that. And then zenith. Zenith is kind of the, as I call it, the new frontier, is the twisting in the relative twisting in the groove. Okay. Now, screen share. All right. But of course, with zenith, we're using the cantilever as our proxy to read the groove, to align, right? Because we can't see the contact edges of the stylus. So
And
the setup goal.
That's what we do when we set up the offset, correct?
Yeah.
So what we're really doing is adjusting zenith. When we call it, we're adjusting offset. We're really doing zenith.
Yeah. Well, when you're aligning the cantilever for proper offset angle, you are aligning the cutter head, and that's it. I'm sorry. When you're aligning the cantilever for proper offset angle, all you're aligning is the cantilever, and we're assuming that the contact edges of the stylus are perpendicular to the cantilever. However, we now know, I now know, I've gotten verification now that 2 of the 3 stylus manufacturers have a tolerance of ±5 degrees.
That's crazy.
And
what are the 3 manufacturers, by the way?
3 major manufacturers are Geiger in Switzerland and Ogura and Namiki in Japan. Okay, so the goal is to remain faithful to the azimuth, zenith, and rake angles of the lathe cutter head. Okay, try to replicate. So the question becomes, what was the cutter head aligned at? Now, there are certainly tolerances that exist when they put the cutter head stylus into the chuck. All right, but one thing that we do know is that 2 of the 3 axes, it's beyond debate what they should be. Okay, azimuth, 90 degrees to the lacquer surface. There's 0 reason why it would be anything else than 90 degrees to the lacquer surface. The zenith would be collinear with the radial line. So this is what we mean by collinear. You just go from the center of the lacquer and draw a line to the edge. The cutter head stylus should be perfectly on that line, not to the side, and certainly not diagonal to it. The image that you see there in the top right is an image taken from a microscope of a cutter head. So with rake, however, no standard exists. There is no standard. In fact, I could make a good argument that the quietest grooves are cut at less than 90 degrees. The science that has been done on the ideal playback angle, however, because when the hot cutter head stylus, which is heated, when it cuts the soft lacquer, the lacquer goes into a semi-liquid liquefied state, And there is something called, once it's cut and cools, there's some spring back. So even if it's cut at less than 90 degrees, it doesn't necessarily mean that that is the mechanical angle at which it bounces back to. More work to be done, but no standard actually exists for playback or for cutting. Okay, I've seen now the best science that's been done on the playback is, of course, the one that was done by Risch and Meyer in 1981 in Audio Magazine, but it's not very robust science. When, of course, they came out with having done intermodulation tests at a number of different cutting houses throughout the US and came back with 92 degrees as being the goal. They didn't say whether that was dynamic or static. And I regularly measure, when I do my analyses, I always measure dynamic. So I know that there can be anywhere from 1/4 degree to 2 1/4 degrees difference between static and dynamic SRA. Azimuth, let's just cover azimuth a little bit. Why do we even care about optimizing it? Ideal azimuth, to answer the question, let me go first. Ideal azimuth, it's not a function of how the stylus or cantilever is oriented to the record. A lot of people think it is. People think, oh, well, if I just align the body, if I align the head shell, it's good to go. No. You can, this is a picture of a cartridge that is ideally aligned for its azimuth angle. Now, we can have a conversation as to whether it left the factory with intolerances, but that's a 2.6 degree angle. And that's not only where it sounds best, that's where it measures best. Okay. Now, remember, I showed you that the anatomy of the stylus that has a major radius. And that major radius offers a degree of forgiveness to allow the stylus to be at an angle, an azimuth angle, at a tilt in the groove, without suffering any mechanical consequences. That's why there's a radius on those sides of those cantilevers. Okay. Go ahead.
So, well, no, you can, I'm sorry, you continue, and then if I'm still confused at the end, I'll ask.
Okay, because if you need me to, I can stop the presentation, show the screen, and show you my stylus. That always seems to kind of help. So changing the stylus's angle in the groove doesn't impact crosstalk. Now, if it's egregious tilt of the stylus, it can cause other problems, but that's for another discussion. So I did an animation in CAD of what really is going on when you're measuring azimuth. So watch this video. All right, so the cantilever, the stylus is actuating at a 45 degree angle, because remember how those record grooves are cut, right channel only, which means that that coil, the white coil, is a right channel, and that's moving in the magnetic field, and that's exciting an electrical signal. And you notice that the red wasn't moving. Now you spin the coils. Okay, if you misalign the coils, the groove wall and the right channel coil are no longer aligned. So now, as you can see, the red, which is the other channel, is moving just a little bit, even though there is no signal in the groove for that coil. Right? Was that clear?
Right.
Okay. All right. So how to optimize azimuth and where to start. By the way, I don't remember if I say it here, but the azimuth is always the last step in your setup process. You got to use electrical measurements. There is no, I'd love to be able to measure it mechanically, because I don't like multivariate tests at all, and I'll go into that a little bit later. But there's no way to visually see and measure the angle of the coils in the magnetic field. So you have to take an electrical measurement. You need a left-right 1 kilohertz signal. You could use various azimuth measurement products like the Fuzzgometer. I think the Fiker is now out of production, I think. I heard that. I'm not sure if it stays. Or you can use a digital multimeter. If you go to the Wally School blog and read the articles I did on azimuth, eventually you'll follow the breadcrumbs and you'll lead to Analog Planet, where Michael's already got the steps to use a digital multimeter. It is the last step to perform in the setup process. Make sure it is. Everything is interrelated in these 3 axes. If zenith is off, I'm going to get a different result for azimuth, my ideal azimuth angle, than if I correct for zenith. Indirect azimuths may need one more step. So what is an indirect azimuth tone arm? So an indirect azimuth tone arm, there are 2 things to consider. An indirect azimuth tone arm will have a straight arm wand, and it will have no, I'm going to stop the share for a minute. Okay, and I'm going to take the camera, and it will have no offset yoke. You see this Kuzma tone arm?
Mm-hmm.
All right, I'll take my gummy thing, sticky stuff. See how the horizontal bearing is at an angle to the arm wand? It's called an offset yoke. That makes this a true azimuth tone arm, not an indirect. This over here, the 4.9, that is an indirect because it does not have an offset yoke. Okay. So those may require one more step. Why?
And a quick question. And with an S-shaped tone arm, is that
that's a true azimuth.
That's true azimuth.
That's true azimuth. An S or a J-shaped tone arm, arm wand is going to be a true azimuth. Yes.
Mm-hmm.
Okay. Am I in the frame? Okay. All right. Go back to the share screen. All right. The one more step is the reason why there's potentially one more step is that on arms that are indirect, when you change azimuth, you're also changing rake. And I got a calculator on the Wally Tools website so that you can play around and just learn. Well, if I do a 1.5 degree azimuth change on my 300 millimeter effective length tone arm, what will my impact be to my rake? So there it is. Test records. Oh God. So recently I did a study of 8 different test records, and I wanted to measure. I was looking for I had a whole completely different hypothesis I was working on. I didn't find what I was looking for, but what I did find is that these 8 different test records gave me completely different answers as to where my ideal azimuth angle should be. The variation from one end to the other was slightly more than 1.5 degrees. Now, 1.5 degrees, azimuth is really sensitive to minor changes, subjectively, right? That blew me away. What does that mean? It means that in these cutting houses and at these lathes, not all these guys are being careful. They're creating a test record. Which one's the right one? Which one was made with a cutter head stylus that was perfectly perpendicular to the lacquer surface? I don't know. I mean, of all the 8 records, and I purchased some more since then, I can tell you where the greatest density is, but does that mean that's where perpendicular is? I don't know.
So, JR, let me back you up one second. You had mentioned that it's the zenith error and the azimuth are interrelated.
Yeah.
And since even in a properly set up tone arm with a properly mounted stylus diamond, it's only going to be perfectly accurate at 2 points, correct?
You mean you're talking about for the zenith?
For the Zenith, right.
Yes.
So now these test records, for instance, I have the acoustic sounds, and the left and right 1K signals are in the second and third bands, which are close to, but not exactly on, the bare wall point.
You're getting it. You're nailing it.
So like, if I set up, I would imagine that where these companies put their test tones on the record is going to make a significant difference then.
Definitely. And few of them are sensitive to that. Yes. And guys, I just back up for a minute. I want to make clear that you see me diving deep here, right? I will never say that if you've got a misaligned stylus that you can't have wonderful, enjoyable music. You can. But as you'll see here, and I'll prove it more, it's a mechanical certainty that if it's not aligned properly and you have a fine line contact stylus, it's a mechanical certainty you won't get all of the information from the groove. And I'll prove it. Okay? So these test records, in addition to having these cutter head stylus misalignments, have huge difference in their amplitude. From the quietest one, which was the Cardis, which is no longer in print and is my favorite, unfortunately, to the loudest one, there's a 16 decibel variation. That 16 decibels is unacceptable. It was way louder than any music that we would play. Why is that a problem? When you've got a higher amplitude, you got a higher coefficient of friction. There's more friction. When there's more friction, there's more skating force. When there's more skating force, what's happening to the cantilever? It's getting pulled over more towards the spindle. And when that happens, your zenith error is getting worse. So I'll go more into skating force and such in a little bit. So yeah, about 1.5 degree variation across 8 test records. So Stylus Rake, I mentioned the Risch and Myers study that says that 92 degrees is the ideal playback based on their intermodulation distortion test, even though I'm suspicious about whether intermodulation distortion tests are even the right way to determine that. There have been other publications in the Journal of Audio Engineering, but most of them focus on the angle of the cantilever, which I don't care about the angle of the cantilever. Within limits, I don't care about it. So. And I mentioned that I think the quietest grooves, we could back this up. Now is not the time for it. The quietest groove would be cut at less than 90. I mentioned the spring back. It's an incomplete science, okay? But, and so this is now, remember that image I showed you early on, the microscopic image of the left channel groove, right? Of the test signal. Now, if you imagine that each one of these, this is an exaggerated view, imagine that each one of those undulations that you saw that were formerly oriented horizontally, now they are represented by these bars oriented vertically. But notice what's happening is that with a rake angle that's different from what the cutter head the stylus was cutting at, what will happen is that the stylus contact edge will skip from peak to peak, okay, rather than reaching down into the undulations. This will only happen at very high frequency, probably only at 33 RPM, and it'll be worse at the inner area of the record. But, and I'll go this a little bit later when we talk about the finite element analysis that we've been doing. We have yet to find a mechanical reason why rake angle should matter. In the mechanical relationship between the stylus and the groove. But we have many, many different variations of groove types to go through yet, but we haven't seen it yet. So far, changing rake angle, what we do see is that when you change rake angle, it'll change the height in the groove at which the stylus will contact the groove. So how do you optimize rake angle? Microscopic inspection only. Again, I'm going to go later why I really don't like multivariate tests. Microscopic inspection is an example of a univariate test where you are measuring only that one parameter, that bit of data that you care about, rather than worrying about other data that will obfuscate the one parameter you care about. So, but it's the dynamic rake angle that matters, not the static, meaning dynamic, meaning what angle does it, when you put a stylus onto a record that's not moving, and then you start the platter spinning, it's going to cause drag, and it's going to cause the cantilever to drop down. Cantilever drops down, well, that changes rake angle. So, and as I mentioned before, I've seen as much as 2¼ degree change between that static and dynamic. That's pretty big. But usually it's in the neighborhood of 1 degree. So it's not that much, but usually in the neighborhood of 1 degree. And I recommend 2 steps for measuring it. The measure the stylus contact edge and its relationship to the cantilever, and then at a lower magnification, and you can even do this with a cell phone, then you measure the cantilever's angular relationship to a moving record surface. So I'm just about to release the Wally scope, and included in the Wally scope is a trimmed record where I go hunting at Goodwill, buy all the garbage, easy listening stuff, and then I put it on my table router, and I route off the outer 5 millimeters or so of the lip. Why? So that you can put the stylus right at the very, very, very edge of the record, and it's in the groove. So that when you take an image with the microscope, the record surface and the stylus and cantilever will be in focus. So yeah, that's an example of the 2 shots that I suggest to take and measure in order to get your dynamic rake angle. The image on the right was taken with the Wally scope on a moving record. Right.